Hi everyone, thanks for tuning back in to our second video on related rates introduction. I just wanted to transfer all that work we did on this side paper. I want to transfer that onto the actual worksheet, so that's what I did. So if you need to, you can just pause the video here and just make sure you have all the pieces and parts. Like I definitely wrote the 3 sentences for sure. Hopefully you can see those. I really just did the majority of the work here up top and then just did my side work and my new fill-ins for parts B and C. So if you pause that, once you have that filled in and you understand that, you can flip this over. I just have a little recipe here that might help you as you're working through related rates problems. I won't take the time on the video to read this because I know you can read, but just go ahead and read that and see how it relates to the step-by-step process that we did on the first video, setting up the highlighted regions here to set up our work. And then the last thing I wanted to address in this video is just something, this is a question that came up, it really only came up once, several years ago, and it was a question I hadn't really thought about up until then. And this is more for my why people. If you're not a why person, if you are totally satisfied and have no questions on your mind about the ladder problem, then you could probably skip this part. But if you're a why person, then perhaps this question may have crossed your mind, because it crossed my mind, and it definitely crossed several students' minds several years ago, so we kind of dug into it. So I'm going to actually write over some of this because the green pen is not popping out here, but let's just look at it. I'm calling this a related rates ladder problem why moment. So here's what it says. The classic ladder problem is a huge related rates hit. But why does dy dt vary while dx dt, the rate at which the ladder is pulled along the ground, a constant? Okay, so here was the question posed by a student several years ago. We had done a ladder problem, so we had drawn the classic ladder picture, and we had assigned this was X, this was Y. And if I use the example of like the 8-foot ladder from the last example, this was 8. And so we were given that dx dt was being pulled, the base was being pulled out at this constant rate. So whoever is pulling this ladder out away from the wall was doing it at a constant rate. So my student said, hey, why isn't the rate at which it's dropping, why isn't that then also constant? It seems like if I pull this at a constant rate, then this should be dropping down the wall at a constant rate. And I had to really think about that. In fact, we all thought about it for quite some time because I was like, nobody's ever asked me that. Yeah, why? Because in theory, it seems like it would work. But here's the answer. And feel free to pause the video if you want to think about it on your own for a little bit. But I wrote here that the answer is simple, and we kind of proved it by example down here. In order to maintain the integrity of the Pythagorean theorem, dy dt cannot be a constant rate when dx dt is a constant rate. Like they both can't be constants. And here's the demo below. So where we started this proof by example is we just drew, I'm going to trace over this. Like I said, it's too light. So we drew this triangle, right triangle. Now, in this example, we had a 20-foot ladder. So this 20 represents the length of the ladder that's leaning up, okay? So what we did is we did that on every picture. So we drew 4 pictures here. And in each picture, we had that same 20-foot ladder. And one more 20-foot ladder, okay? So that's what was the same. Now, what we did is we took snapshots. First, when the base of the ladder was 4 feet from the wall, when the ladder was 6 feet from the wall, when the ladder was 8 feet from the wall, and when the ladder was 10 feet from the wall. Okay, so do you see how the change in x with respect to time, or dx dt here, okay, change in x over time, dx dt, is 2 feet per 1 second. Oh, here we go again with these announcements.
If you purchased a photo package on Picture Day, August 30th, and are unhappy with your pictures, please bring your package and report to the auditorium. If you are a new student or a student that didn't have your photo taken, or you did purchase a package and would like to do so now, please bring your order form and payment envelope with you to the auditorium. Again, 11th grade students M through Z. Thank you.
Okay, so, lost my train of thought here. So we're at 4 feet, 6 feet, 8 feet, and 10 feet. So you see how it's changing here? X is changing. So X, dx dt, is changing 2 feet, and we're going to assume per second. That's the model we're setting up here. So we're going 2 feet per second. Okay, now, how does that affect y? Well, let's keep the Pythagorean theorem rocking here. So that's what this is. So we took each triangle with 20 and 4, 20 and 6, 20 and 8, and 20 and 10, and we just used Pythagorean theorem to find y when x is that value. So for this one, it was y squared plus 16 equals 400. We subtracted the 16 to get 384, and we square rooted to get 19.596. Then we did it with 20 and 6. So y squared plus 36 is equal to 400, and y squared 364, and so y 19.079. Then we did it with these measurements, 20 and 8, so y squared plus 64 equals 400. Y squared, subtract that 64, you get 336, square root, and you get 18.330. And finally, with a 20 and a 10, y squared plus 100 equals 400, y squared equals 300, and square root to get 17.321. So we knew that x was changing. So the change in x over time was 2 feet each second. Now, my y values. This one's 19.596, 19.079, 18.330, 17.321. How quickly are these decreasing with respect to time? Well, that's what I did over here. So the first change in y with respect to time is 0.517. So if I take 19.596 minus 19.079, I get a change in y over time of 0.517 feet per second. If I take 19.079 minus 18.330, then that change in y, 0.749 feet per second. And one more time, if I take 18.330 minus 17.321, then that change in y with respect to time is 1.009 feet per 1 second. So you can see, in order to keep the integrity of the Pythagorean theorem and to have a constant dx dt, dy dt cannot be constant. So that proves why when one of your rates here in this example is fixed, the other one cannot be. And that's why we have all these different answers coming out for parts A, B, and C. So hopefully that makes sense if you're a Y person. Thank you for watching, and now you can do your mastery on ladder problems.